Okay. Well, this is 6.5, other counters. And counters can be designated to generate a desired sequence of states. Divide by n counter, also known as modula n counters. A counter goes through a repeated sequence of n states. Sequence may follow binary count or may be any other sequence. Counters used to generate signals to control sequence operations in digital system. Counters can also be constructed by means of shift registers. In this section, we'll present a few examples of non-binary counters. Now, this is a counter with unused states. Circuit with n flip-flops has 2 to the n binary states. There are occasions when a sequential circuit uses fewer than this maximum possible number of states. States that are not used and specified in the sequential circuit are not listed in the state table. In simplifying the input equations, the unused states may be treated as don't care conditions or may be assigned specific next states. It's important to realize that once a circuit is designed and constructed, outside interference during its operation may cause the circuit to enter one of the unused states. In that case, it's necessary to ensure that the circuit eventually goes into one of the valid states so that it can resume normal operation. Otherwise, if the sequential circuit circulates among unused states, there will be no way to bring it back to its intended sequence of state transitions. If the unused states are treated as don't care conditions, then once the circuit is designed, it must be investigated to determine the effect of the unused states. And the next state from its unused state can be determined from analysis of the circuit after it's designed. Now, as an illustration, consider the counter specified in table 6.7. The count has a repeated sequence of 6 states with flip-flops B and C repeating the binary count 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1, 1, 0, and I felt expected to go to 1, 1. Sure enough, it doesn't. 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 0. So it's alternating back and forth like that. So flip-flop A alternating between 0 and 1 every 3 counts. Count sequence of the counter is not straight binary, and 2 states, 0, 1, 1, and 1, 1, 1 are not included in the count. Basically, the two options where you have 1, 1 for B and C. The choice of the JK flip-flops results in flip-flop input conditions listed in the table. Inputs K sub B and K sub C have only 1s and X's in their columns. K sub B and K sub C, which is right here. So these inputs will always be set to 1. Because it doesn't matter what these are. So it's just as easy to make them all 1s. The other flip-flop equations can be simplified by using min terms 3 and 7 as don't care conditions. And the simplified equations are given with this. K sub C is always equal to 1. K sub B is always equal to 1. These have a mixture of 1s and 0s. J sub A would equal to B because it's 0, 0, 1, 0, 0, 1. And here we got 0, 0, 1, and these don't matter. K sub A is equal to B2, I think. Yeah. Because we got the pattern 0, 0, 1, and we have the 0, 0, 1 here. And since these three don't matter up here, then we can set this equal to B. 0, 1, 0, 1. That would be C. Because notice here we got 0, 1, 0, 0, 1, doesn't matter. And then 0, 1, 0, 0, 1, 0. So J sub B is equal to C. That's equal to 1, we said. That's equal to 1. J sub C. 1, some, nothing, 0. 1, nothing, 0. Let's see. J sub C is equal to B prime. Is that true? B prime would be 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0. Sure enough, that's B prime. I didn't see that one. But these are simplified equations that can easily be seen, relatively, except for B prime, directly from comparing this against your present state. Okay. Now, since there are two unused states, we analyze the circuit to determine their effect. If the circuit happens to be state 011 because of an error signal, the circuit goes to state 100. 011 would follow this, and the next state is 100. After the application of a clock pulse, because again, that's the order it's going in. This action may be determined from an inspection of the logic diagram by noting that B is equal to 1. The next clock edge complements A and clears C to 0. And when C is equal to 1, next clock edge complements B. In a similar manner, we can evaluate the next state from present state 111 to be 000. And they present that over here. So if it does fall out of here, our normal would go from 110 to 111, so it just continues on its normal path. And same down here. 010, the next one, binary wise, would be 011. So if it was there, then it would, the next one after that would be 100. So you can think of it that way. The state diagram, including the effect of the unused states, is shown in the figure I just looked at. If the circuit ever goes to one of the unused states because of an outside interference, the next count pulse transfers it to one of the valid states, and the circuit continues to count correctly. Thus, the counter is self-correcting. The self-correcting counter, if the counter happens to be in one of the unused states, it eventually reaches a normal count sequence after one or more clock pulses. An alternative design could use additional logic to direct every unused state to a specific next state. Now, a ring counter. Timing signals that control the sequence operation in the digital system can be generated by a shift register or by a counter with a decoder. A ring counter is a circular shift register with only one flip-flop being set at any particular time. All others are cleared. A single bit is shifted from one flip-flop to the next to produce the sequence of timing signals. One flip-flop to the next to produce is shifted. Okay, it's shifted. Now, if the initial value is 1000, then when I shift it right, this would become a 100, and this would become a 0. Shift it again, this is a 1000, and that's just seeing with the loop here, with the ring counter. That's pretty obvious here. You have your voltage going up to 1 here. That's there. Here it's the 1. Here it's the 1. And here's the 1. And since we've been shifting this over, then this goes back to 1. Let's see. Initial value of the register is 1000, requires a preset clear flip-flops. Single bit is shifted right with every clock pulse and circulates back from T3 to T0. Each flip-flop is in one state once every 4 clock cycles. That makes sense. Produces one of the 4 timing signals shown in the figure we already looked at. Each output becomes a 1 after the negative edge transition of the clock pulse, and remains 1 during the next clock cycle. For an alternative design, timing signals can be generated by a 2-bit counter that goes through 4 distinct states. The decoder shown in figure 6.17 decodes the 4 states the counter generates the required sequence of timing signals. To generate 2 to the n timing signals, we need either a shift register or 2 to the n flip-flops or an n-bit binary counter together with the 2 to the n line decoder. For example, 16 timing signals can be generated with a 16-bit shift register connected as a ring counter, or with a 4-bit binary counter and a 4 to 16 line decoder. In the first case, we need 16 flip-flops. In the second, we need 4 flip-flops and 16 4 input and gates for the decoder. It is also possible to generate time signals with a combination of a shift register and decoder. That way, the number of flip-flops is less than that in a ring counter, and decoder requires only 2 input gates. Combination is called a Johnson counter. And that's what we have here. Grab a drink. Okay. K-bit ring counter circulates a single bit amount of flip-flops to provide K distinguishable states. Number of states can be doubled if the shift register is connected as a switch tail ring counter. Switch tail ring counter is a circular shift register of the complemented output of the last flip-flop connected to the input of the first flip-flop. Figure 6.18 shows a shift register. 6.18A. So you got all these coming out here. A is going in there, B is going in there, C is going in there, and then there's with the switch tail ring counter is a circular shift register with the complement output of the last flip-flop. Okay, I was wondering why these weren't complemented. So the last one is one that's complemented, and it's sent back into our first one. The circular connection is made from the complemented output of the rightmost Come to the rightmost flip-flop to the input of the leftmost flip-flop. That's right there. Register shifts its contents once to the right with every clock pulse. And at the same time, the complement value of the E flip-flop is transferred into the A flip-flop. Starting from a clear state, the switch tail ring counter goes through a sequence of 8 states. That's it. I don't need to read that. First off, 0, 0, 0, 0. So got all these as zeros. Well, this one is being complemented, so this is going to a 1, and that feeds back into here. And that's why the A becomes a 1. Then all the rest of these are still 0. And then this 0 gets complemented, comes around here, so that's why we have 1, 1. And so when it does that, it just keeps putting a 1 on the front. It gets down to this point, this one is shifting to the right, so it's taking its complement, which becomes 0. And then all of a sudden you have 0, 1, 1, 1, and so forth. Okay, Johnson counter is a K-bit switch ring, switch tail ring counter with 2 times K decoding gates to provide outputs for 2K timing signals. The decoding gates are not shown in figure 6.18, but are specified in the last column of the table. Yeah, I didn't see where this came from. So the decoding gates are not shown, but are specified in the last column. The 8 AND gates listed in the table and connected to the circuit will complete the construction of the Johnson counter. So this is how you do the Johnson counter. Since each gate is enabled during one particular state sequence, the output of the gates generate 8 timing signals in succession. The decoding of a K-bit switch tail ring counter to obtain 2 times K timing signals follows a regular pattern. The all 0 state is decoded by taking the complement of the 2 extreme flip-flop outputs. Two extreme flip-flop outputs. I guess that makes sense. If this was 0 and this was 0 initially, no, this shifts, but then this one wouldn't. But if I went and did that, this would change, or I don't see the 2 extreme. I see it from the AND gate breakdown here, where you got A prime and E prime, but I don't see it from this diagram. But again, they said they weren't providing all the detail. The all 1 state is decoded by taking the normal outputs of the 2 extreme flip-flops. All other states are decoded from an adjacent 1, 0, or 0, 1 pattern sequence. For example, sequence 7 has an adjacent 0, 1 pattern, flip-flops B and C. Decoded output is then obtained by taking the complement of B and normal output of C or B prime C. One disadvantage of the circuit is that if it finds itself in an unused state, it will persist in moving from one invalid state to another and never find its way to a valid state. The difficulty can be corrected by modifying the circuit to avoid this undesirable condition. One correcting procedure is to disconnect the output from flip-flop B that goes to the D input of flip-flop C, and instead enable the input of flip-flop C by this function. So D sub C is equal to A or C and B, where D sub C is the flip-flop equation for the D input of the flip-flop C. Johnson counters can be constructed for any number of timing sequences. The number of flip-flops needed is only 1/2 the number of timing signals. The number of decoding gates is equal to the number of timing signals, and only 2 input gates are needed. Okay, 6.6. Registers and counters can be described by an HDL at either the behavior or the structure level. Behavioral modeling describes only the operation of the register as prescribed by a function table without a preconceived structure. A structural level description shows a circuit in terms of a collection of components, such as gates, flip-flops, and multiplexers. The various components are instantiated and connected to form a hierarchical description. The design similar to a representation of the multi-level logic diagram. Examples in this section will illustrate both types of descriptions. Both are useful. When a machine is complex, a hierarchical description creates a physical set partition machine in the simpler and more easily described units. Four-bit universal shift register. Okay, here it is. It's on page 337. I was seeing serial, but I wasn't seeing parallel. Got a register output. A par 3:0. PAR, I guess that's for parallel. And here's our parallel outputs here. Now, I par is our parallel inputs, which corresponds to these down here. So these are coming in, those multiplexers. We also have select inputs, S1 and S0, which is over here, S1 and S0. We got our most significant bit, least significant bit, in MSBN, LSBN. That's up here. That's for each one of these shift registers. We have that coming in, and have that coming in. And then we got our CLK and clear B. Our clock, which is right here, and our clear B. And down here, we got our it's not in diagram, but if clear B is equal to 0, then our A parameter, we're going to be bringing in, what's that called, zeros. For this one, down here, we got the case 0, 0, and A parameter is equal to A parameter, which is what this is indicating over here. It's all zeros, there's no change. Now, if we got 0, 1, it's this right here. 0, 1 tells us we're going to shift right. And that makes sense because we've got a most significant bit, because most significant bit is coming in here and shifting it. Shift left, then our least significant bit is on this side, and we're shifting it. And then a parallel load takes complement of those, looks like. Well, no, it's 1, 1, and it's equal to 1, the input, which is 1, 1. Okay, we're just going to look at the Verilog. No, we won't look at all these. This is another universal shift register on page 359, so I'll skip over that. EHDL, synchronous counter. This is on bottom of page 362. 6.14b. Okay, so this is our 6.14b. We've got our I's coming in, we've got our A's going out, so input and output. So here's our data output. Input is data in. That's our eyes over there. We got C out, which is down here. We got count, load, CLK, and clear B. Count, load, CLK, and clear B. CLK, clear B is up here. Okay, based upon our table, well, if not clear B, so if 0, that's this first case where it's 0. So it does not matter. Else if load, okay, I'm not sure if I follow those, but Verilog, that's practice, VHDL, VHDL, that's it. Okay. Plug that. Okay, now I'll put the Chapter 6 test out. And the final project will be to finish up the remaining labs for the course. We did some of them early on, and I saved some of them because I was had in mind that it'd be good for the final project. Down here, we have 3 more class periods, 25th, 2nd, and 4th. We don't have any class on week from today. That's our Thanksgiving break. Now, I won't be covering any material in these 2 days, but if you have any questions, then I'll be on Zoom. Won't answer any questions on the final project or test, of course, but those will be out there. These remaining 2 weeks, you can work on the final project, the last test. You can work on anything from the beginning of the semester. So if you haven't done something, then you can still turn that in. Now, the last day to turn in anything for the course is December 6th. So after that period of time, I won't accept anything. That gives me the final exam week to get to grade everything that you've turned in. Don't leave any item not turned in. I haven't put zeros out there for assignments you have not turned in because Blackboard has a weird quirk. If I put a 0 there and you turn it in, I grade it, it will save it as a 0 unless I go and fix it. I have to revert to previous grade, which makes no sense. My big worry is that I'll forget to choose revert to previous grade and you'll get a 0 for something you turned in. Again, do not leave anything not turned in. I recognize this is kind of hideous material. A lot of you still haven't finished chapter 1 and 2 test. So I've kind of held off on that. And you can still do those. Again, if you need something open, just let me know and I'll open it back up. Otherwise, we're at the end, and this will give you some time to to finish up any remaining projects. I'm gonna go ahead and stop the recording now, and then I'll be online the rest of the time if you have any questions.